Here is the second problem that I want to talk about. What happens to the unit ball in Rn? Well, for n equal to 1, volume, let's say, of the unit ball. For n equal to 1, it is minus 1 to plus 1, 1 dx1. That's the volume of the unit ball in one space is simply the set of all points whose square is less than or equal to 1. So that is equal to 2. For n equal to 2, V2 is equal to integral 1 dx1 dx2 over x1 square plus x2 square less than or equal to 1. And that is simply the unit disk. And the formula, and we know already explicitly what that is equal to, pi. For n equal to 3, V3 is 1 dx1 dx2 dx3, the Riemann integral of this continuous function over the set of all x1 squared plus x2 squared plus x3 squared is not equal to 1. And the volume of that is simply equal to 4 by 3 pi r cube, r is 1, so that's equal to 4 by 3 pi. Now if you look at 2 is less than pi, pi is approximately 22 by 7, and pi is clearly less than 4 by 3 pi, so it looks like the volume is increasing, but boom, the volume really goes down. So, claim, so it looks like V of n is increasing with n. Not so, not true. V of n goes to 0 as n goes to infinity. In fact, V of n goes to 0. So I will write down explicitly the theorem. So theorem is the following. V of n plus 1 is delta n times Vn, that is definition, and delta, if you let V of n plus 1 be equal to this, then square root of n times delta sub n goes to square root of 2 pi. That requires some analysis from Gauss distributions, and then B is that for every eta positive, P sub n over n, eta to the power n goes to 0 as n goes to infinity. 3C, V of n times n factorial to the power n factorial to the power 1 over n converges to 2 pi, square root of 2 pi as n goes to infinity. These are the three results about this. And this fact that V of n goes to 0 as n goes to infinity, computer scientist John Hopcroft at Cornell thinks that it's a very deep result. That is, it's not expected by the volume of the unit ball to go to 0, but it happens. Now, one more theorem I want to state is that let V of n comma p be equal to 1 dx1 dx2 dxn over S and p consists of all vectors x, which is coordinates x1, x2, xn, whose LP norm 1 to n, a mod xi to the power p, I equal to 1 to n, is less than or equal to 1. Let S and p be equal to this. Yes. Let B and P. Then the claim is the following. V1P is 2, Vnp for any n is going to be V1P times pi delta Jp, j equal to 1 to n, where delta Jp is equal to minus 1 to plus 1, 1 minus mod x1 to the power p to the power n over p this is wrong, so I'll correct it. So let me state the following result. Then V1p equal to V and A, this is B, or is the following: Vn times n factorial to the power 1 over p raised to 1 over n goes to C of p 0 less than C of p less than finite. Again, let me conclude with a reference to this paper. This is by just myself, resonance, and the page numbers are 320. Where does it begin? Yeah, here it is. 334 to 340 in the month of April 2008.
In B,
Yes?
is it Vn by n raised to n?
No, n factorial to the power 1 over p raised to the power 1 over n. This b.
No, not that B.
Oh, here. Yeah, for every eta positive, Vn over n, eta to the power n goes to 0.
N raised to n.
Eta raised to n. For any eta positive.
Okay.
So for any eta positive, so Vn dies faster than any power of n, any power of eta.
Much.
Very rapidly. Whereas you look like, in the beginning everything is increasing. So if you are a physicist, you would conclude that Vn is increasing. Not so. Vn is going to 0 very rapidly. Okay, so then the last paper that I want to talk about is an introduction to probability theory. And this was done by the great Russian mathematician Kolmogorov. He wrote a book called Introduction to Probability Theory, Axiomatic Foundation of Probability Theory in 1929. Just then, the great Lebesgue had constructed an extension of length of an interval to arbitrary sets which are called Lebesgue measurable sets. And this Kolmogorov saw that and borrowed that idea from him. So I will describe briefly what is the structure of probability spaces. This is what is probability theory, and I will give you the reference also on this. So what is probability theory? Probability theory is concerned with the following four notions. One is that of an experiment where the outcome is not predictable ahead of time. For example, if I throw a stone at height, it will fall down. And if I observe it falling down or not, that experiment has a deterministic outcome. On the other hand, if you measure the temperature outside this hall at noontime tomorrow and ask you to predict what the temperature is going to be, that's not going to be possible. The prediction will be, you will have to present an interval. It will have to be specified. That's a random phenomenon. So, that's the notion of experiment. And then the sample space, so this is called a random experiment. It consists of four notions. This is called sample space, the set of all possible outcomes. Set of all possible outcomes. And then a collection B of subsets of the power set of omega. And then the fourth element is P, B contained in the power set. The power set of omega is the set of all possible subsets, set of all subsets of omega. You notice that if omega is a finite set or consisting of n possible outcomes, then the power set has 2 to the power n possibilities. But if omega is already countably infinite, then the set of all possible subsets of a countable set is uncountable. So very quickly, the sigma algebra B becomes a huge one, uncountable from finite case and to jumps to uncountable case. And P is a function from B to 0, 1 such that P is a measure. P of the empty set is 0, P of the whole space is 1, P is what's called countable additive. So every probability problem can be identified with an experiment, a sample space, a sigma algebra of what are called events, and then a set function P, which is a probability measure. And you have to specify these 4 quantities to specify a probability space. So every probability theory is probability experiment consisting of these things. So 4 objects. And let me give you examples of these things. The simplest example is consisting of 2 points. Example, omega consists of only 2 outcomes, 0, 1. B is going to be the power set, namely 0, 1, 0, 1, and then the empty set. Those are the 4 possibilities. And then P of 0 is equal to P, and this is 1 minus P, and then this is 1, this is 0. 0 less than or equal to P less than or equal to 1. So that's the model for coin tossing. So any experiment which leads to 2 possible outcomes. And then this is example 1. Example 2, omega is a finite collection of outcomes, 0, 1 to k less than infinity. B is going to be the power set of omega, and that has the cardinality of B of omega is 2 to the power k plus 1. There are k elements, k non-zero elements. If you add 0, then k plus 1 elements. And then every probability measure P is specified by what it gives to singletons. P of 0, P of 1, P of 1. So P is determined by P of 0, P of 1, or P of k. So all that you have to specify here is one number. Here you have to specify k plus 1 numbers, which are non-negative and adding up to 1. And that will specify the distribution. But here the sigma algebra consists of 2 to the power k plus 1 elements. And you can go on with the case that the next case would be omega equal to countably infinite case, 0, 1, 2, 3, infinity. For example, if you count the number of insurance claims made in a given period, the insurance claims can be as little as nothing, 1, 2, 3, etc., large number. That's example 3. And then B is going to be the power set of omega, which is going to be uncountable. And then the probability measure P is specified by what it does to singletons, P of 0, P of 1, P of 2, etc. So in other words, a collection of numbers P0, P1, P2. So you have to specify a sequence of positive numbers, Pi, or non-negative numbers, which add up to 1. Pi non-negative, summation Pi equal to 1. 0 to infinity, Pi equal to 1. An example of that would be what's called the Poisson distribution. Pi is e to the minus lambda, lambda to the power I over I factorial. Example, Pi equal to e to the minus lambda, lambda to the power I over I factorial, I equal to 0, 1 to infinity, and lambda between 0 and infinity. The fact that summation lambda to the power I over I factorial is exactly e to the power lambda will help you prove that summation Pi adds up to 1. So that's an example. And now you can give more continuous examples, and For example, so let me give you one more example. For omega to be R and B to be the Borel sets of R and P to come from the Gauss distribution. P of A is equal to integral over A e to the minus x squared by 2 dx 1 over square root of 2 pi, A belonging to B of R. It requires to prove, so there is a need to show that minus infinity to plus infinity e to the minus x squared by 2 dx is exactly square root of 2 pi. And I'll leave that as an exercise. See if we can prove that. That's not easy to prove. And associated with every probability distribution on the real line is a notion of what's called CDF. So let me write down what CDF is. A cumulative distribution function. A CDF is a function f from R, real line to 0, 1, such that 1, it has the following property: x1 less than or equal to x2, x1, x2 belonging to R, implies f of x1 less than or equal to f of x2, that it is non-decreasing, and 2, for every x belonging to R, f of x plus equal to f of x, namely the right continuity, and 3, f of minus infinity equal to 0, f of plus infinity is equal to 1. F of minus infinity by definition is the limit of f of x as x goes to minus infinity. And this by definition is limit as x goes to plus infinity of f of x. They exist because f is monotone. So we want these properties, and then there is a theorem due to Lebesgue and Stieltjes, LS theorem, is the following: given a CDF, capital F on R, there exists a probability measure Pf on R, the Borel sets, such that Pf of any, A, B is equal to f of B minus f of A. So you give me a distribution function and go to sleep. I will construct for you a probability measure on the Borel sets of the real line. That's Stieltjes theorem. If you take, P to be uniform distribution on 0, 1, then you'll get, Lebesgue already constructed it, but this is more general than this thing. And that's why it's called Lebesgue-Stieltjes theorem. Lebesgue Stieltjes theorem. Stieltjes was a mathematician, and he lived in Europe, maybe in Holland perhaps. Stieltjes. And Lebesgue, of course, is a French mathematician. Okay, so then there are two important theorems on probability theory, and I will state them theorem to you, and then I will quit with that. Two major results in probability theory. One is called the law of large numbers, LLN. Let x1, x2, xn be a sequence of random variables on some probability space, such that the probability that x1 belongs to A1, x2 belongs to A2, xi belongs to AI, I equal to 1 up to n, 1 up to k is the product of the probability of I equal to 1 to k, probability xi belongs to AI. That's what IID means. Then, and let the integral of mod x1 dp over omega be finite. Then x1 plus x2 plus xn The ergodic theorem holds x1 plus x2 plus xn converges with probability 1 to expectation, the integral of x1 dp over omega with probability 1. This is the law of Rod's numbers. This can be deduced from the ergodic theorem of Birkhoff, but it is more general than that. Then I will also state the central limit theorem. Central limit theorem requires a more hypothesis, namely, well, the word central limit theorem was coined by the great Polya, CLT, that x1, x2, xn be such that x1, x2, xn are IID, independent, identically distributed random variables for every n, such that expectation of x1 is equal to 0, that is the integral of x1 dp over omega is 0, and the expectation of x1 squared equal to the integral of x1 squared dp over r over omega is finite. Then for every a comma b, a b belonging to r, a less than b, the probability that square root of n times x1 plus x2 plus xn or x1 plus x2 plus xn over square root of n lies between a and b. This is a quantity that depends on n, converges as n goes to infinity to integral a to b 1 over square root of 2 pi e to the minus x squared by 2 dx. For every a less than b less than minus infinity less than a less than b less than plus infinity. So those are the main results of probability theory. And again, let me give you a reference. 3 is the following. KBA, what is probability theory? And in pages PP 292 to 310, in what year? April 2015, resonance. So in fact, you can get all of my papers by going to the website www.ias.ac.in. Go and then click on journals. Click on resonance. Click on authors and then type KB Athreya. Then you will find all my papers from since 1997 till 2017. So I'll stop right here. Is that good enough?